There was a time when the newspapers said only 12 men in the whole world understood the theory of relativity. I never believed that. There might have been a time when only one man did, because he was the only guy who caught on before he wrote his paper. But after people read Einstein's paper, plenty of people understood relativity. Certainly more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. Now, I said that. I meant it. And I said it in front of a room full of very smart people at Cornell during a set of lectures in 1964. And you might think, well, that's a strange thing for a physicist to say, because here I am, a guy who uses quantum mechanics every single day. I calculate with it. I make predictions with it. I built a good chunk of my career on it. So what do I mean? Nobody understands it. That's the puzzle I want to investigate with you today. Not quantum mechanics itself, not yet, but what it means to say that nobody understands it. Because I'll tell you something, most people who hear that quote walk away with completely the wrong idea about what I was getting at. And the wrong idea they walk away with tells you something very interesting about how the human mind works, and about what we expect from nature, and about the deepest trouble in all of physics. So let's be detectives. Let's treat my own words as a crime scene. What did I actually mean? Let me lay out the suspects one at a time, and let's see which one holds up. And I'll tell you right now, the answer we find is going to lead us somewhere unexpected, somewhere that connects to the biggest unsolved problem in all of physics. But we have to earn that. First, the suspects. The first suspect is the most popular one. Almost everyone grabs this one first. They hear, nobody understands quantum mechanics, and they think, oh, he means the math is too hard. The equations are too complicated. It's all Greek letters and abstract nonsense, and you need a genius brain to follow along. And look, I get why people think that. If you've ever glanced at a quantum mechanics textbook, you've seen the wave functions, the Hilbert spaces, the bracket notation, the operators. It looks like an alien language. So the natural assumption is that Feynman, good old plain-talking Feynman, was just admitting that even for the experts, the mathematical machinery is overwhelming. But that doesn't hold up, not even for a second. Because here's what I know about the math of quantum mechanics. It works spectacularly well. You write down Schrödinger's equation, you solve it for a hydrogen atom, and out pop the energy levels, and those energy levels match the lines you see in the spectrum of hydrogen to an absurd number of decimal places. You use quantum electrodynamics, the theory I worked on myself, and you can calculate the magnetic moment of the electron to better than 10 decimal places. And the experiment agrees. 10 decimal places. That's like predicting the distance from New York to Los Angeles and getting it right to the width of a human hair. So the math isn't the problem. The math is, if anything, the one part we're completely confident about. Physicists use this math every day and it never lets them down. Chemists use it. Engineers building transistors use it. The entire semiconductor industry, every transistor ever built depends on quantum mechanical calculations that come out right. If nobody understood the math, none of that would work. But it does work, every time. Suspect number one, the math is too hard, doesn't fit the evidence. Throw it out. All right. Suspect number two, maybe what I meant is that we don't have enough experimental data. Maybe quantum mechanics is like a half-finished map. We know some corners of it, but there are big blank spaces. Maybe I was just saying, look, we haven't tested it thoroughly enough, so we can't claim to really understand it. This one doesn't survive either. In fact, it's even worse than the first suspect. Quantum mechanics has been tested more thoroughly than any theory in the history of science. Not just tested, brutalized. For decades, people have tried to find an experiment where quantum mechanics gives the wrong answer. Not because they hate the theory, but because finding a crack in it would be the most important discovery in physics. It would win you the Nobel Prize so fast your head would spin, and nobody has found that crack, not in 90 years of looking. Every prediction quantum mechanics has ever made, when calculated carefully and tested honestly, has come out right. Atomic spectra, molecular bonds, superconductivity, lasers, the behavior of semiconductors, the properties of superfluids, the Lamb shift, the anomalous magnetic moment, the Casimir effect, tunneling through barriers. Every single one. In the late 1970s and the 1980s, people tested something called Bell's inequalities. Let me tell you briefly what that's about, because it's important. The story goes back to 1964, when a physicist named John Bell, an Irishman working at CERN, asked a very sharp question. He said, suppose quantum mechanics is wrong, and underneath all this probability business, particles really do have definite properties all along. Suppose there are hidden variables, secret little notes each particle carries in its pocket, telling it how to behave in every possible measurement. If that were true, what would we expect to see? And he proved, mathematically, that any such hidden variable theory would have to obey a certain inequality, a limit. The correlations between measurements on two separated particles could never exceed a certain value. Then he showed that quantum mechanics predicts correlations that violate that limit. Quantum mechanics says you can get correlations that are stronger than any hidden variable theory allows. So the question became, which is right? Is nature playing by the hidden variable rules, or by the quantum rules? Starting in the early 1980s, Alain Aspect and others ran the experiments. They measured correlations between pairs of photons, separated by enough distance that no signal traveling at the speed of light could pass between them during the measurement. And the results violated Bell's inequality. They matched quantum mechanics perfectly. Nature is as strange as quantum mechanics says. There's no comfortable, hidden, common-sense explanation lurking below. Not unless you're willing to accept something even stranger, like influences that travel faster than light, or a universe where the future affects the past. So suspect number 2 is dead. We have mountains of data. More data than we have for almost anything else in physics. Lack of evidence is not the problem. Let me bring in suspect number 3. This one is subtler. Some people hear my quote and they think, well, that's just Feynman being humble. Or Feynman being cute. He's a showman. He likes to say dramatic things. And nobody understands quantum mechanics is a great line for a lecture. Gets a laugh. Puts the students at ease. Don't worry, kids. Even the great Feynman doesn't get it. And I'll admit there's a grain of truth to this. I did want to relax the audience. I was about to describe some very strange things, and I wanted people to stop trying to force those things into familiar boxes. I literally said right after that line, do not keep saying to yourself, but how can it be like that? Because you'll get down the drain into a blind alley from which nobody has escaped. So yes, there was a pedagogical purpose, but if you think the whole thing was just a rhetorical flourish, you've missed it. You've missed the most important word in the sentence. And that word isn't nobody. It isn't quantum. It isn't mechanics. The word is understands. That's the real clue. That's where the case breaks open. Everything hinges on what you mean by understand. Let me show you what I'm getting at. And to do that, I need to take you through the single most important experiment in all of physics. The experiment that, more than anything else, reveals why quantum mechanics is the way it is. The double-slit experiment. You've probably heard of it. But let me walk through it carefully, because the devil is in the details, and the details are where the trouble lives. Here's the setup. You have a wall with 2 narrow slits in it. Behind the wall, you have a screen that can detect where particles land, and you have a source that fires particles, one at a time toward the wall. Start with something ordinary. Bullets. Imagine you have a machine gun that sprays bullets somewhat randomly toward the wall. Some go through the left slit. Some go through the right slit. The rest hit the wall and stop. On the screen behind, you get 2 clusters of bullet holes. One cluster behind the left slit, one behind the right slit. Makes perfect sense. Each bullet goes through one slit or the other and lands accordingly. Open both slits, and the pattern on the screen is just the sum of the 2 individual patterns. Nothing surprising. Now do it with water waves instead. You have a pond and you drop a pebble to make ripples. The ripples hit the wall, pass through both slits, and on the other side they spread out and overlap. Where the peaks of 2 waves meet, you get a bigger wave. Where a peak meets a trough, they cancel. On the screen, you don't get 2 simple clusters. You get an interference pattern. Bright bands where the waves reinforce each other. Dark bands where they cancel. Very different from the bullet pattern, but completely understandable if you know how waves work. All right, now the main act. Do it with electrons. Fire electrons, one at a time, at the double slit. Each electron hits the screen and makes a tiny dot. Just like a bullet, 1 dot, 1 electron, 1 click on the detector. So far so good. But here's what happens when you fire thousands of electrons, one at a time, and look at where all the dots accumulate. You do not get 2 clusters, you get an interference pattern. Bright bands and dark bands, exactly like the water waves. And that's already very strange, because each electron arrived as a single dot, a single particle. It didn't spread out like a wave. It went click. Right there, one spot. But somehow over thousands of individual clicks, the pattern that emerges is a wave pattern. So you might think, okay, maybe each electron is secretly a little wave, and when it hits the screen, the wave collapses to a point. Weird, but maybe I can live with that. But wait, here comes the part that really hurts. You ask, well, which slit did the electron go through? Perfectly reasonable question. It's a particle that made a dot. It must have gone through one slit or the other, right? So you set up a little detector at one of the slits. A tiny light, say, that flashes when an electron passes through. Now you can tell which slit each electron went through, and the instant you do that, the interference pattern vanishes. Gone. You get two simple clusters, just like bullets. Let me say that again, because I want you to feel the full weight of it. When you don't look at which slit the electron goes through, you get the wave pattern. When you do look, you get the particle pattern. The act of finding out which slit it went through changes the result. This is not a matter of clumsiness. It's not that the detector bumps the electron and ruins things. People have tried every conceivable way to be gentle, to minimize the disturbance, to sneak a peek without touching. It doesn't matter. Any method whatsoever that gives you information about which slit the electron went through destroys the interference pattern. The universe seems to have a rule. If you can know the path, no interference. If you cannot know the path, interference. And if you think that's strange, let me make it worse, because there's a version of this experiment proposed by John Archibald Wheeler that is even more disturbing. It's called the delayed choice experiment. Here's the idea. You fire your electron toward the double slit. You let it pass through, and then after it has already passed through the slits, you decide whether or not to detect which slit it went through. You make the choice late, after the electron has supposedly already decided whether to be a particle or a wave, and it still works. If you choose to detect the path after the fact, the interference pattern vanishes. If you choose not to detect the path, the interference pattern appears. The electron seems to have known retroactively what you were going to decide. Now, you have to be careful about how you describe that. It does not literally mean the future is affecting the past. But it does mean that you cannot think of the electron as having chosen a definite behavior at the slits. The electron does not become a particle at the slits and then stay a particle. It does not become a wave at the slits and then stay a wave. What the electron is between the source and the screen is not determined until the entire experiment, including your measurement choice, is complete. Wheeler used to say, no phenomenon is a phenomenon until it is an observed phenomenon. And he meant that quite literally. The experiment has no definite outcome, not even a definite past, until the measurement is actually made. If that doesn't bother you, think about it again more slowly. Now, sit with that for a moment, because this is where the trouble starts. In classical physics, the physics of everyday life, we understand things by building pictures, models, stories about what's happening when we're not looking. The ball is at the top of the arc. The planet is on the far side of its orbit. The gas molecules are bouncing around in the box. We have a mental movie of what's going on behind the scenes, and that movie is consistent, and it makes predictions, and those predictions match what we see. This is what understanding feels like. You can close your eyes and picture the thing. You can run the mental movie forward and predict what happens next. You have a mechanism, a story, a picture of what is going on. And the double-slit experiment says you cannot do that for quantum mechanics. Not because you're not smart enough, not because you need better instruments, but because there is no consistent classical picture of what the electron is doing between the source and the screen. Think about it. If the electron goes through one slit, you should get the bullet pattern, but you get the wave pattern. If the electron goes through both slits, well, how does a single particle go through two slits? And if you try to check, the pattern changes. The electron seems to refuse to have a definite story about what it did. This is not a failure of imagination. People have tried every possible picture. The electron is a particle that secretly goes through both slits. The electron is a wave that collapses when observed. The electron takes all possible paths simultaneously. The universe splits into two copies. Each of these ideas has been explored, debated, published, and picked apart by very brilliant people for the better part of a century. And none of them is universally accepted. None of them can be proven to be the one true picture. Because quantum mechanics, the actual mathematical theory, does not tell you what the electron is doing between measurements. It tells you the probability of where you'll find it when you look. That's all. And that's enough to make all those spectacularly accurate predictions I mentioned earlier. But it doesn't give you a picture. It doesn't give you a mechanism. It doesn't give you a story you can close your eyes and watch like a movie. And that right there is what I meant. When I said nobody understands quantum mechanics, I was not complaining about the math. I was not lamenting a shortage of data. I was not performing false modesty. I was making a precise statement about a precise problem. We do not understand quantum mechanics in the way we understand other theories. We do not have a mental picture of what is happening at the quantum level. We have rules that tell us what we will observe when we measure, and those rules work perfectly. But behind the rules, behind the calculations, there is no story, no mechanism, no picture that everyone agrees on, and that doesn't lead to paradoxes. Understanding in the deepest human sense means being able to say, here is what's happening and here is why. In quantum mechanics, we can say, here is what will happen, but we cannot say why, and we cannot say what is happening in between. That is what nobody understands. Now let me go further, because the problem is even deeper than the double-slit experiment suggests. The double slit is just the doorway. Behind that doorway is a whole landscape of trouble. Consider measurement. In quantum mechanics, a particle can be in what we call a superposition. An electron spin, for example, can be in a state that is neither up nor down, but some combination of both. Not that we don't know which it genuinely is both, in a very precise mathematical sense. The amplitudes for up and down are both present. Then you measure the spin, and you always get a definite answer. Up or down, never both. The superposition is gone. You got one result. What happened? How did the superposition become a definite outcome? What is the mechanism? Schrödinger himself saw this trouble coming. He was one of the architects of quantum mechanics, and he was deeply uncomfortable with the implications of his own theory. So in 1935, the same year as the EPR paper, he cooked up a thought experiment designed to make the absurdity vivid. You put a cat in a box. With the cat, you put a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter clicks, the vial breaks, and the cat dies. If the atom doesn't decay, the cat lives. Simple enough. But the atom, according to quantum mechanics, doesn't have a definite state until you measure it. After 1 hour, the atom is in a superposition of decayed and not decayed. And since the fate of the cat depends on the atom, the cat is supposedly in a superposition too. Alive and dead at the same time. Now, nobody actually believes the cat is both alive and dead. Schrödinger didn't propose this because he thought it was a reasonable description of reality. He proposed it to show that something must be going wrong when you extend quantum rules from atoms to cats. Somewhere between the atom and the cat, the superposition must resolve into a definite outcome. But where? And how? That is the measurement problem in its purest form. At what point does the quantum blur become a classical fact? Is it when the Geiger counter clicks? When the vial breaks? When the cat dies? When you open the box and look? When a friend asks you what you saw? Quantum mechanics, the bare mathematics, does not answer this question. It gives you the superposition and shrugs. Well, the honest answer is, we don't know. Not really. This is called a measurement problem, and it has been open since the 1920s. Every interpretation of quantum mechanics has a different answer. The Copenhagen interpretation, which is the one most textbooks teach, says, don't ask. The wave function collapses when you measure, and that's that. Don't look for a mechanism. There is no deeper story. Just accept the rules. Many worlds' interpretation says the superposition doesn't actually collapse. The universe branches. In one branch, you got spin up. In another branch, a copy of you got spin down. Both are equally real. Neither knows about the other. Pilot wave theory says there was a definite answer all along, carried by a hidden wave that guides the particle. The particle always had a position, we just couldn't see it. But yet, spontaneous collapse theories say the wave function really does collapse randomly on its own, according to some new physical process that nobody has ever directly detected. Each of these interpretations is consistent with the experimental data. Every single one of them gives the same predictions for every experiment we've ever done. You cannot design an experiment, at least not yet, that would rule one out and confirm another. They are empirically equivalent, and they give you wildly different pictures of reality. In one, the universe branches into countless copies. In another, the electron always had a definite position, guided by an invisible wave. In another, wave functions spontaneously collapse. In yet another, there is no story at all, just calculations. That is an extraordinary situation. We have a theory that predicts the results of every experiment we throw at it, and we have no agreed-upon picture of what the theory is telling us about the world. In Newtonian mechanics, we understand what the theory says about reality. Objects have positions and velocities. Forces push them around. We can picture it, we can close our eyes and watch the movie. Take general relativity, we understand what the theory says about reality. Space and time are a fabric, mass curves the fabric. Other objects follow the curves. It's hard to visualize perfectly, but we have a coherent picture, and it works. And notice something. Relativity is strange. Extremely strange. Time runs slower in a gravitational field. Moving clocks tick differently. Lengths contract. None of that matches everyday experience. When Einstein first proposed it, people found it bizarre. Some refused to accept it. It violated common sense in the most fundamental ways. But here's the difference. Despite all that strangeness, relativity gives you a picture, a strange picture, a mind-bending picture, but a consistent, visualizable picture. You can draw diagrams, you can trace world lines through space-time. You can see in your mind's eye how the curvature of space-time guides the motion of planets. The picture defies your intuition, but it replaces your old intuition with a new one. After enough work, you develop a relativistic intuition. The strangeness becomes familiar. Quantum mechanics does not do that. No amount of study gives you a quantum intuition in the same sense. You can become very skilled at calculating. You can develop a feel for which way the amplitudes will point. But you never get a picture of what's happening between measurements. That picture doesn't form because there's nothing to form it from. The theory doesn't offer one. That's the crucial difference. Relativity is strange but picturable. Quantum mechanics is strange in a deeper way. It refuses to give you any picture at all. We have competing pictures, none of which we can confirm, each of which is strange in its own way, and the bare formalism, the math by itself, won't pick one for us. Consider what this means. It's not that the theory is incomplete. The theory is absurdly successful. It's that the theory is complete in its predictions, but silent about its meaning. You calculate. You get the right answer. You ask what's actually happening, and the theory looks at you and says, I told you what you'll see. What more do you want? And we say, we want to understand. The theory says, that's your problem, not mine. Let me give you another angle on this, because I want you to feel it from a different direction. Think about what happens when you learn classical physics for the first time. You learn about gravity. An apple falls because the earth pulls it. Fine, you can picture that. You can imagine the force. You can feel it in your bones because you've been living with gravity your whole life. When Newton gives you the mathematical law, the law simply sharpens what your body already knows. Now think about electromagnetism. It's a step harder. You can't feel magnetic fields the way you feel gravity. But you can see iron filings line up along field lines. You can picture the field spreading out from a charge. It's more abstract than gravity, but you can still build a mental image that maps onto the math. Quantum mechanics doesn't give you that luxury. There is nothing in your everyday experience that behaves like a quantum system. Not really. People try analogies. They say an electron is like a cloud, or it's like a wave on a pond, or it's like a coin that's spinning in the air. Not yet heads or tails. And every single one of those analogies breaks down the moment you push it. The electron isn't like a cloud because a cloud is made of tiny droplets in definite places, and the electron cloud isn't like that at all. The wave isn't like a water wave because the quantum wave function is a wave of probability amplitude, which is a complex number, which has no direct analogy in the physical world you can touch. The spinning coin is just a case of ignorance. You don't know if it's heads or tails, but it is one or the other. A quantum superposition is not like that. It's not ignorance. Both possibilities are genuinely present in the formalism. An entanglement breaks analogies even further. Two entangled particles separated by any distance are connected in a way that has no classical counterpart. Measure one and the other responds, not because a signal passed between them, not because they agreed in advance. The correlations are too strong for any prior agreement to explain, as Bell proved. And yet no energy, no information, no physical signal crosses the gap. People try analogies for this too. They say it's like a pair of gloves. You put one in a box and send it to Tokyo, the other to London. When you open the box in Tokyo and find a left glove, you instantly know the London box contains a right glove. Nothing mysterious about that. But But entanglement is not like gloves. With gloves, the leftness and rightness were decided when you packed the boxes. The answer existed all along. With entangled particles, Bell's theorem proves that the answer did not exist all along. The correlations cannot be explained by pre-existing properties. The analogy breaks. Every analogy breaks. Because the quantum world is not a strange version of the ordinary world. It's a different kind of world entirely. Our everyday concepts are not just imprecise descriptions of quantum reality. They're the wrong categories altogether. It's as though you're trying to describe music using the vocabulary of flavors. You can say a melody is sweet or sharp, and those words carry a dim echo of truth, but they are fundamentally the wrong tools for the job. That was the point I made in those lectures. An atom does not behave like a miniature solar system with little planets going around in orbits. Nor does it behave like a cloud or fog of some sort. It behaves in its own inimitable way, which technically could be called a quantum mechanical way. It behaves in a way that is like nothing you have seen before. Your experience with things you have seen before is incomplete. The behavior of things on a very tiny scale is simply different. And understanding, the deep, intuitive, bone-level understanding, the kind where you can close your eyes and watch the movie, requires something to map the theory onto. It requires a picture drawn from experience. And nature, at the quantum level, refuses to provide one. That's not a temporary embarrassment. It's not something that will get fixed when we're smarter or have better technology. It's a fundamental feature of the situation. The quantum world does not owe us a classical picture. Let me tell you something else that I think is important. This problem, the problem of what quantum mechanics means, is not something physicists have been ignoring. It's not a dark corner that nobody has explored. It's been the subject of intense debate since the very beginning. Einstein didn't like it. He spent the last 3 decades of his life arguing that quantum mechanics must be incomplete. There had to be deeper variables hidden from us that would restore the kind of picture he wanted. A picture where things have definite properties whether you look at them or not. In 1935, Einstein, together with Boris Podolsky and Nathan Rosen, published what is now called the EPR paper. It's one of the most important papers in the history of physics, and what it argued was this: quantum mechanics says that 2 particles that have interacted can become entangled. Once entangled, measuring one particle instantly tells you something about the other, even if they're on opposite sides of the galaxy. You measure the spin of particle A and find it pointing up. Quantum mechanics says particle B's spin is now definitely pointing down right at that instant, no matter how far away it is. Einstein said, look, either the information traveled between the particles faster than light, which violates relativity, or particle B already had a definite spin before you measured it, and quantum mechanics just didn't know about it. And since faster than light signals are absurd, the particles must have had definite properties all along. Quantum mechanics is incomplete. There are hidden variables. He called the faster than light option spooky action at a distance. He meant it as an insult. That cannot be how nature works, he said. Bohr disagreed. He said, no, the lesson of quantum mechanics is that you can't separate the object from the measurement. The question, what is the electron doing when nobody is watching, is not a meaningful question. The properties don't exist independently of observation. You cannot speak about what particle B has until you specify what measurement you're going to perform and on which particle the entangled pair is a single quantum system, and carving it up into 2 separate things with separate properties is exactly the kind of classical thinking that quantum mechanics tells you to abandon. They argued about this for years. At the Solvay conferences, in private letters, through published papers, Einstein would propose a thought experiment meant to show that quantum mechanics was absurd. Bohr would stay up all night, sometimes in great distress, and find the flaw in Einstein's argument. It went back and forth for decades. The Bohr-Einstein debates are among the most profound intellectual exchanges in the history of science. 2 of the greatest minds who ever lived, staring at the same experiment and coming to opposite philosophical conclusions. And here's the thing. Both of them were using the same mathematics. Both of them could calculate. Both of them got the right answers. They disagreed about what the answers meant. That disagreement has never been fully resolved. In the 90 years since, the debate has grown richer and more sophisticated. We have new interpretations, new no-go theorems, new experimental tests that constrain the options. But we still do not have consensus. Working physicists disagree today, right now, about what quantum mechanics is telling us about reality. Some say it tells us that reality is fundamentally probabilistic. Things genuinely don't have definite properties until they're measured. A second camp says it tells us that reality has a deeper level with hidden variables that we haven't found yet. Still others say it tells us that the universe constantly splits into branches and every possible outcome occurs somewhere. Then there's the most radical camp, which says it doesn't tell us about reality at all. It's a tool for making predictions. Asking what it means is like asking what a hammer means. You don't understand a hammer by finding its meaning. You understand it by using it. That last view, the shut up and calculate approach, is actually what a lot of practicing physicists adopt in their daily work. And it's effective. You can spend an entire career doing brilliant quantum physics without ever committing to an interpretation. Just compute, check against experiment, publish, repeat. But there's something unsatisfying about it, because we're not just calculation machines. We're humans. We want to know what's going on. We want the movie. We want the story. And quantum mechanics, uniquely among all our theories, says, I'll give you everything except that. Now I want to stop here and turn this around on you. Because I suspect most of you listening to all this are secretly thinking, come on, Feynman, surely someone will figure it out. Give it another 50 years, 100 years, and some genius will crack it. They'll find the picture. They'll explain what the electron is really doing. Right? Maybe. But let me suggest something more unsettling. What if the problem is not with physics? What if the problem is with you, with the human brain? What if our demand for a picture, for a mechanism, for a story of what's happening, is a biological accident, a quirk of how primate brains evolved to track predators and find food on the African savanna? What if the universe has no obligation to be the kind of place that fits inside a skull? That possibility should genuinely unsettle you, because it means there might be a ceiling on human understanding. Not a temporary ceiling, a permanent one, built into our hardware. So where does this leave us? It leaves us in one of the most fascinating situations in the history of human knowledge. We have the most successful theory ever devised. It has never been wrong. It undergirds all of modern technology. And it does not tell us what the world is like when we're not looking. This is not a problem to be fixed, or at least it might not be. It might be that the demand for a classical picture, the demand that nature should make sense in terms of stories and pictures drawn from everyday life, is simply a human prejudice, an expectation born from the fact that we evolved in a world of medium-sized objects moving at medium speeds, where things do have definite positions and velocities, where causes precede effects in a straightforward way. The quantum world doesn't operate that way. And maybe understanding needs to be redefined. Maybe understanding doesn't mean having a mental movie. Maybe it means something else. Maybe it means being so fluent with the formalism that the math itself becomes your intuition. The way a musician doesn't think about individual notes anymore. They think in phrases and textures and shapes of sound. A jazz pianist, after enough years of practice, doesn't calculate which notes go with which chord. The fingers just know. The music flows without conscious reasoning. And if you ask that pianist to explain in words why a particular passing note sounds right in a particular context, they might not be able to give you a satisfying answer. They might just say, it sounds right. I've heard enough music, played enough music, that my fingers know what the harmony wants. Is that understanding? In some sense, yes, it's a deeply functional understanding. It produces correct results. It responds appropriately to context. But it's not the kind of understanding where you can draw a diagram and say, here is why this note goes here. Maybe quantum mechanics demands that kind of understanding from us. A musician's understanding. Fluency without explanation. Skill without a picture. Maybe that's enough. Or maybe it's not, and someone will find the picture someday. I'll confess something. When I work on quantum mechanics, I don't try to picture what the electron is doing. I think in terms of amplitudes. Probability amplitudes are complex numbers, and they combine in specific ways, and the rules for how they combine are the rules of quantum mechanics. Add the amplitudes first, then square to get the probability. That's the rule. And when I apply that rule, I get the right answers. Let me show you how strange this rule is, because it's the key to everything. Suppose an electron can reach a certain spot on the detector by two different paths. Path A and path B. In ordinary probability theory, the kind you use when flipping coins or rolling dice, you'd say the probability of arriving is the probability of taking path A plus the probability of taking path B. Simple addition. More paths means more probability. The chance of arriving can only go up when you open a second route. But in quantum mechanics, each path has an amplitude, not a probability. And amplitudes are different. They have a magnitude and a phase, like an arrow that points in a particular direction. When you add two amplitudes, the arrows can point the same way and reinforce each other, or they can point in opposite directions and cancel each other out. So in quantum mechanics, opening a second path can make the probability of arriving go down, even to zero. Think about that. You have an electron that can reach the detector by going through slit A. You open slit B, giving it an additional route, and now it can't reach the detector at all. The two paths cancel. The amplitudes add up to nothing. That's interference. That's the dark bands in the double-slit pattern. And there is no classical picture, no story about particles or waves or anything you've ever seen that makes this seem natural. In the everyday world, more routes means more arrivals. In the quantum world, more routes can mean fewer arrivals. The math that describes this is beautiful and precise. But the intuition, the gut feeling, the mental movie, it's nowhere to be found. Do I understand why that rule is true? No, I know the rule. I know it works. I can use it with great skill. But I cannot explain why nature decided that the fundamental quantities should be amplitudes, complex numbers that you square to get probabilities, rather than just probabilities directly. There is no deeper story I can point to, and I've made my peace with that. Not happily, not with satisfaction, but with a kind of honest acceptance. The theory tells us what will happen if we set up certain experiments, and it keeps its word with extraordinary precision. But it won't tell us what's happening in the privacy of its own home. Now, if you're the kind of person who finds that frustrating, good. You should find it frustrating. That frustration is the engine that drives people to explore new ideas. Maybe someday someone will find a deeper theory that underlies quantum mechanics and provides the picture we're missing. Maybe someone will discover that one of the interpretations is actually right and prove it with an experiment nobody has thought of yet. That would be wonderful. That would be one of the greatest achievements in the history of thought. But maybe not. Maybe quantum mechanics is the deepest level, and the lack of a classical picture is not a defect but a feature. Maybe nature just doesn't work the way our brains expect, and the right response is not to demand a better story but to update our expectations. I've always thought the key is what I said right after the famous quote, I said, do not keep saying to yourself, but how can it be like that? Because you'll get down the drain into a blind alley from which nobody has escaped. Nobody knows how it can be like that. That's the deepest form of not understanding. It's not that the math is hard. It's not that the data is missing. It's that the question, how can it be like that, has no answer. Or rather, it has many possible answers, none of which we can confirm, all of which are strange. And what I wanted people to do, what I still want people to do, is to stop demanding that nature explain herself in familiar terms. Accept what she does, learn the rules, get comfortable with the amplitudes, and then stand back and appreciate just how astonishing it is that we can predict the behavior of atoms and photons and electrons with such breathtaking accuracy, even though we cannot draw a picture of what they're doing when nobody is watching. That's not a failure. That's one of the most profound discoveries human beings have ever made. We discovered that the universe operates on principles that don't match our everyday intuition, and yet we found the mathematical language to describe those principles precisely. We can speak nature's language, we just can't translate it into our own. That gap between the formal language that works perfectly and the everyday intuition that fails completely is what I meant when I said nobody understands quantum mechanics. The formalism does the work. We ride along on top of it, and we have to be satisfied with fluency without the feeling of understanding. And you know what? That's not so bad. Because the universe is bigger than our intuitions. It always has been. Every revolution in physics has forced us to give up some comfortable assumption. Copernicus took away the center of the universe. Darwin took away our special place in biology. Relativity took away absolute time. And quantum mechanics took away the very idea that things have definite properties when nobody is looking. Each time people resisted. Each time they said, it can't be like that. And each time nature said, it is. And I'll tell you something else. This problem, this inability to understand quantum mechanics in the deep sense, may not be just a philosophical nuisance. It may be blocking our path forward. Right now, the biggest unsolved problem in fundamental physics is how to combine quantum mechanics with general relativity. Einstein's theory of gravity describes space and time as a smooth, curved fabric. Quantum mechanics says everything at small scales is fuzzy, uncertain, subject to superposition. When you try to smash these two ideas together, the math breaks. You get infinities. You get nonsense. And some people, smart people, think the reason we're stuck is precisely because we don't understand what quantum mechanics is really telling us. If we had the right picture, the right mental framework, the right understanding of what the quantum world is actually like, maybe the path to quantum gravity would become clear. Maybe the reason the two theories don't fit together is that we're carrying a wrong assumption from one of them, an assumption we can't identify because we don't understand the theory well enough. That's speculative, I'll grant you, but it's suggestive. The lack of understanding isn't just a cosmetic problem. It might be a roadblock. So the next time you hear somebody say nobody understands quantum mechanics, don't take it as a confession of defeat. Take it as the starting point of the deepest adventure in physics. The math works, the experiments confirm, but the story, the picture, the mental movie of what's really happening, that remains the great open question, and it may be the key to the next revolution. Personally, I think that's the most exciting thing about physics right now. Not the questions we've already answered, not even the questions we know how to answer, but the questions we don't even know how to ask properly yet. What is quantum mechanics trying to tell us about the nature of reality? We don't know. Nobody knows. And that's not a reason to despair. That's a reason to get out of bed in the morning. You know, people sometimes ask me, doesn't it bother you? You're spending your life working with a theory you admit you don't understand? And I say, no. It delights me, because it means the adventure isn't over. It means nature still has secrets, deep ones, and we're just getting started. The fact that we found equations that predict the behavior of atoms to 10 decimal places without understanding why those equations work is one of the most astonishing things that has ever happened in the history of human thought. We've learned to speak a language we don't comprehend. We've cracked a code without knowing what it means. If that doesn't excite you, I don't know what will. And should we demand more from our theories than correct predictions? What does it really mean to understand something in physics? Those are questions worth arguing about, and I'd like to hear your thoughts.